Hi everyone, this is lesson 2.6, Electrophilic Addition Mechanism. Again, this is adapted from the PSH's Chemistry 3 module lesson 2.6. For this lesson, we have two targets. First, to draw the mechanism for an electrophilic addition reaction, and second, to determine the reactants given the addition products. So we will start the lesson with this reaction. NH3 or ammonia reacts with BH3 forming this compound. So we are asked to determine which among the reactants in the given reaction is the electrophile and which is the nucleophile. So recalling from the definitions of these terms, or simply from how we would like to remember them easier, an electrophile would be a structure that loves electrons. On the other hand, a nucleophile, something that is drawn to a positive charge. So we would expect electrophiles to be electron deficient, and therefore that would be this structure, BH3, because it lacks an octet. The central atom lacks an octet. On the other hand, the nucleophile would have either a lone pair or an excess negative charge, and that would be, in this case, ammonia. So here are the nucleophiles and the electrophiles in the structure. Next, using full-headed arrows or curved fishhooks, draw the mechanism of the reaction. So starting from this illustration, we can simply trace the path of the electrons coming from, as we can see, this lone pair is going to be shared between nitrogen and boron. So we draw the arrow coming from the lone pairs here going to boron. So that's it for the simple recall. Let's proceed to the main topic, which is electrophilic addition. So this reaction proceeds in two steps with a planar carbocation intermediate. So this illustration is found in your module. As you can see, in simple inspection, it proceeds in two steps. And also notice that the reaction mechanism is drawn in a very straightforward manner. It hasn't been broken apart into two separate steps, but rather it looks like a flow chart from start to finish. So we're going to break this apart into its component steps. First, we have the reaction between ethene and HBr. So first, let's take a closer look at the structure of ethene, represented by its hybridized orbitals as well as the remaining p orbitals or the unhybridized p orbitals responsible for the pi bond. Again, this is ethene, and this is the illustration showing the orbitals. So notice that each carbon has a trigonal planar structure around it from the degenerate sp2 hybridized orbitals, because we have three groups around each carbon. And then for each carbon, we have two sp2 hybrid orbitals forming a sigma bond or a head-on overlap to the hydrogen atoms. And then it also forms a sigma bond or a head-on overlap between between these two carbons, and there is a sideways overlap between the remaining unhybridized p orbitals forming the pi bond. So let's proceed to the first step in the reaction mechanism. Electrophilic addition happens when the pi electrons from the nucleophilic bond of ethene attack and abstract a proton from HBr. So this is HBr. The pi electrons here would have a negative charge, therefore they're nucleophilic in nature and would attack the partially positive charge in the polar bond of HBr. Remember that bromine is an electronegative atom. Therefore, it pulls electrons towards itself. Therefore, this end becomes partially negative. This end becomes partially positive. So, the module and most other books would describe the movement of electrons. So, the electrons of the pi bond are described as nucleophilic, which would attack this electrophilic part of HBr. So that is where the electrophilic addition gets its name. So this structure or HBr is added, then the hydrogen part of HBr is electrophilic, and it's the first part of the structure that gets added here, as you will see later. So again, the nucleophilic pi bond here attacks the electrophilic H plus in HBr. And there's a heterolytic bond cleavage in HBr and the formation of a bromide ion. Now, these two processes are shown using these full-headed or double-barbed arrow. So from the pi bond here, the electrons are transferred to H plus here, and the heterolytic bond cleavage or the acquisition of 2 electrons of this bromine atom is also shown by the arrow. And the result of that would be a carbocation intermediate. So what happens is that the carbon adjacent to where the H plus was added gains a positive charge as one of its p orbitals is vacated. So here, notice that this carbon has already acquired the hydrogen from HBr. Therefore, it already has 4 groups around it, and it now has an sp3 hybridization with a tetrahedral structure around it. On the other hand, this other carbon, which has lost an electron, still has 3 groups around it. Therefore, it is still sp2 hybridized with a trigonal planar shape around it. However, it still has the p orbital, which is unhybridized, but this time it's empty. And because of that, it has a net positive charge, making this structure a carbocation. And then we can see here the bromine atom acquiring the negative charge, becoming a bromide ion. In the second step, the bromide ion acts as a Lewis base and donates a pair of electrons to the carbocation. So this has a net positive charge, this has a net negative charge, so they're going to attract each other and produce a neutral product. So that is described by this arrow, the movement of electrons from bromide to the positive part of the carbocation, forming another bond. So this is now the final product. So without looking at the mechanism, we simply find that the HBr has added to the double bond, cleaving the pi bond and producing 2 sigma bonds. Okay, so important things to remember for the mechanism of the electrophilic addition in alkenes would be that first, the electrophilic group is the first one to attach to the double bond structure here, and then the more electronegative group comes in second or enters the structure or the substrate second. So there. Now here are other addition reagents, possible addition reagents. So it's not just HX. We can have other HX structures where we have HCl, HBr, HI. Also, we can have other structures like these. And for these structures, there's a corresponding electrophile moiety and a nucleophile moiety. So in this case, H is considered the electrophile moiety and Br is considered the nucleophile moiety. This is because this bond is polar, therefore this becomes partially positive, therefore it's electrophilic, and then this part is partially negative, therefore it's nucleophilic. So the electrophilic part is the first one to be attacked by the pi electrons here, and then the nucleophile moiety is the second one to get attached to the substrate after it has become a carbocation. So that ends the lesson. We proceed with some examples from the navigate part of the module. So draw the products for each of the following sets of substrate and reagent. Using curved arrows, show the mechanism for the reaction. We have these two reactions. And if you can still recall, we are supposed to show the movement of electrons from the nucleophilic pi bond to the electrophilic moiety of the addition reagent. And then because of that, this bond will undergo a heterolytic cleavage, forming these products. After these intermediate products have been formed, there's another movement of electrons to attach the nucleophilic moiety of the reagent to the carbocation that was formed, forming the final product. And for the second example, notice that it's no longer HX, but rather it's actually water. So this happens in the presence of an acid catalyst. So if we would follow this same mechanism, then it should look like this. Double the pi bonds, the electrons from the pi bond here gets attracted to this electrophilic moiety, and then there's a heterolytic bond cleavage forming a carbocation, and the remaining nucleophilic moiety involving a transfer of electrons and then forming the final product. So again, these are the intermediates and these are the final products. Now it just so happened that for this reaction, water, this is the addition of water happening in acidic medium. So in all practical sense, from these two reactants, this product will form. Okay, however, notice that in this reaction mechanism as written, there's the presence of OH. And in real scenarios, this will not happen because the medium is acidic. Therefore, what we do is simply to add an H plus to the HOH, OH minus species. So in this case, what happens is that this molecule does not actually react with water. Instead, it reacts with H3O plus, well, which is actually just H2O with an extra H plus, simply because the environment is acidic. So H3O plus, which can be represented by H with a bond OH2 plus. So this is H3O plus anyway. So this pi bond is gonna attack this hydrogen, and then this bond is going to be cleaved And then instead of the OH minus here, because this bond was cleaved, we will be left with H2O. And now this H2O, the lone pair from oxygen, will be attracted to the H plus or the carbocation here, to the excess positive charge here coming from the carbocation. And then it's going to result to this structure releasing an H plus. Okay, so here's just a closer look at H2O. So the electrons actually come from the lone pair here in oxygen, attacking the carbocation here. And only the OH part gets attached because the H plus gets released anyway. Okay, so this is what actually happens in real scenarios. But again, the first solution that I showed you would suffice for our purpose of understanding the mechanism. So that would be this one. Okay, so in the teacher's guide or in the answer key of your module, this is actually what happens in reality. Again, I'm not expecting you to really know this. Nevertheless, the point of the reaction is that from these two reactants, you produce this product. So for the rest of the graded part of the navigate section, so here are the two other items. So how do we draw the mechanism? So in this case, you'll have just one product because whether H or Br attaches to this carbon or this carbon, you're going to have the same product. So we only have one product for this. For the second process, there's a possibility of having two products. So initially, hydrogen can possibly attach to this carbon or to this carbon. So depending on where the hydrogen moiety attaches first, then it would result to bromine attaching to either this carbon or this carbon as well. So we're going to have two possible products for this. Next, for the not part, propose a substrate and a reagent from which the following compounds can be formed through electrophilic addition. So here, you can actually choose to start with a substrate with a double bond here or there or there, right? So I will leave it to you to decide which starting substrate is best. So you can have the double bond here or here or here. But one of them would result to just one possible product, and that would be the best substrate to start the reaction with. Number two, we have this structure with the Cl attached to this carbon. So we can have the double bond either here, here, or here. Notice that they're symmetrical as well. Therefore, you can just have one starting product, one starting reactant. And then here for bromine, this is attached here and it looks like the parent is symmetrical as well. So you can decide you can only decide between two possibilities, either here or here. Yeah, anyway, having a double bond here or here would just be equivalent. So letter B, using curved arrows, show the mechanism for the formation of A2 through electrophilic addition from the identified substrate and reagent. So when you draw the mechanism, it's a fairly straightforward question. So you can start with whatever reactant you have answered from here, and then there's no water involved. It's just the reactant. The reagent that you'll be using would most likely be an HX. Therefore, um, the mechanism would be straightforward. So with regards to the specific reagents that you can use, you may refer to the previous slide showing the different reagents with electrophilic and nucleophilic moieties, so that uh, will help you decide which reagent to use. So that is all for this lesson. Again, I hope that this has helped you understand the module. Goodbye, class.